We are given a foundation. It's going to be a square shape. The dimension as b and b. The force let's call force as m from now on. And moment. M and M. SPTN is 15. And gamma 18. And let's assume there is no water table. Meter cube. And let's assume the foundation is embedded. This is gonna be sand. And let's assume as 3 meters. Embedment df as 1 meter. So by considering this, we will utilize the Excel sheet. And we will set all our properties here. So let's start with M, eccentricity E. Let's say this is the applied zone. Applied actions. And this side is going to be the capacity of soil. What do I have? N. I have gamma, unit weight. SPTN. Gamma. And let's go back to our table for this. Bearing capacity, lecture notes. We will utilize this formula, so you can simply copy paste the formula by taking a screenshot of the picture for you to remember in Excel. I just copy it and paste it here. I'm looking for NC, N gamma, and NQ. So first I need to correlate and observe internal friction angle. On our lecture notes, we have a correlation factor. It's somewhere here. Our SPTN is about 15, so in between 10 and 20. We will observe something like 31. So for 31, decrease, let's write this to Excel. SPTN 15, this is 18 kilonewton. By 31, and you're looking for NC and gamma NQ. But because this table doesn't give you the exact value in between 30 and 35, then you should utilize this chart. If I copy paste this chart on my Excel, I'm looking for thirty. Remember, this is gonna be linear in y-axis, but logarithmic in x-axis. So for NC, this is the top margin. NC is assumed to be as 41. Use this. And on the other hand, NQ and N gamma is somewhere here. So let's assume that as 28 and this as 41. So 41 and the other two 28, 28. So let's go to our table. Our type of soil is sand. Means the cohesion is equal to 0. So in that case, the first component will be 0. Let's give values to m and n from the example. 10,000 kilonewton. and 200 kilonewton meters. The eccentricity will be equal to moment divided by the axial force. And the unit for that will be meters. Remember, we have a condition for our stress. It has to be eccentricity has to be less than 1/6 dx. So I will copy paste this as well. These are all in your lecture notes. So the left side will be your applied actions, and the right side will be your capacity. Let's write the applied actions in terms of B. To apply equal to into a blank cell. Design axial force. So you need to utilize factor of safety. Factor of safety as 3. Equal to 3 times, watch here, axial force division of the foundation size B squared, which I don't know B yet, so I will assume a blank cell for B. Say B squared in my formula times, open the bracket, 1 plus 6 times the eccentricity E, division of B again. Close the bracket and say yes. Just because you divide with 0, it won't give you a solution now. So this cell I defined initially as B, and it will be in terms of meters. Let me write this. This is gonna be Q applied. So if it's 1 meter, you just give values. It will be kilonewton meter square. So kPa in other words. This is the applied zone. But what you should do, you should also calculate the capacity of soil on the right side until you manage a safe level. So Q capacity will be equal to our formula here. We said initially the first component is going to be 0. So gamma, we assumed it's a dry soil, there is no water. Gamma times embedment depth, it was 1 meter, times 1, times NQ plus 0.4 times gamma times the foundation size B, the foundation size B, which is here. So the bearing capacity increases as you increase foundation size. That's why you need to utilize the same B for both sides times n gamma. And click enter. The unit you have here is also kilonewton divided by meter square, kilopascal. Our condition is that we must satisfy Q applied to be less Q capacity. Until we satisfy this condition, we will increase this. So let's say 3 meters. We still don't satisfy. 6 meters. It's too much. The difference is too much. I'm trying to be close to this. Close, but this one to be bigger. Say 5. Say 4. Not enough. 4.5. 4.6. 4.7. So 4.7 satisfies, and the capacity is slightly bigger than Q applied. A rectangular foundation, not a square shape. So let's take the same actions we have initially. From here and create another one. The rectangular foundation formula is slightly different. Instead of B only, you also have L, which is the long dimension of the foundation. May I ask Shahbaz Sadiq, can you mute your microphone, please? So let's input the values as 10,000 kilonewton. Moment, it was initially 200 kilonewton meter. In these boxes, there will be an iterative method so that we can solve for E dimension. For E, remember, I say plus or equal in Excel. It means you're about to start a formula. I think I'm gonna mute some students. Okay, so if you say equal, it means you started a formula. Remember what was the eccentricity? Moment, I click on moment, division with the actual force. And the unit of that will be meters. What else I need on the applied side? Because I have a moment, my stress distribution, applied stress distribution will be something like this. I'm interested in maximum stress, so I will utilize the formula for the maximum stress. You have bx and by in the formula. By represents the L distance, longest distance. So let's write our formula here. Means factor of safety 3 times the applied axial force applied stress. Let's write it here so that we can compare. The applied stress will be equal to the design axial force with the safety factor division with B times L, close the bracket, times, open the bracket. I will zoom in here. I need some of your friends to be on mute. Daniel Kadar, can you please mute your microphone? Yes, thank you. Open bracket, 1 plus 6 times eccentricity, division with E again, close bracket, and say yes. Let me zoom in and show you what I did. I simply utilized the formula given here. Just because I divide with 0, it gives me an error. We can start giving some values to start with. Of course, these dimensions will be in meters. And it will be kPa in both sides. Remember to keep your microphone muted all the time. This is the stress that you apply. Now let's see what is your capacity on the other side. The capacity will utilize the formula here. Remember we had SPT from the first question. It was 15. SPTN is a result. Some students ask me questions. And SPTN is the site investigation technique which is utilized initially before we start design. Then what other parameters we have? Gamma, the unit weight, it was 18. For your assignment, for your project, I will give you those parameters and I will ask you to create an Excel sheet like this. And 5, it was 31, the corresponding, it was sand. So let's create our bearing capacity here. So let's keep these two as blue and these two as red, so that you understand what I mean. They equal, and write all this formula you have here. Because it's sand, it doesn't have the first component, If it was clay, you would utilize the cohesion in the first component equal to gamma times embedment depth. From the previous video, it was 1 meter. This is the one, 3 meter sand with 1 meter embedment depth. Times NQ. We need to utilize those first. NQ and gamma from the initial calculation. Both of them are 28. Zaghi coefficients. NQ plus 0.5 times gamma again times the B dimension times N gamma times, open the bracket, 1 minus 0.2 times B divided by L. Close the bracket. And final. Our idea is to keep capacity greater than the applied stress. So what I'm going to do, I'm going to play with B and L until I reach the appropriate capacity level. Let's say 2 by 3. It didn't help. 5, 7 for L. 9 for L. As you see, an increase in L, it doesn't really help in the capacity. But if you change B, it helps too much. So 3 by 9 will satisfy my applied pressure in the moment. Okay, this is the stress component. If you have any question now, please ask me.
Excuse me, sir.
Yes.
So we will be given with these parameters like B and L in the plan, or we are supposed to do by ourselves, like starting from the minimum value.
You always start from the minimum value, which is 1 meter in width. Okay? So you keep increase the value. This is for a single foundation, by the way. Later, we will study next week a continuous foundation or a raft foundation where the dimensions are given. So you will calculate some other parameters. So you start from 1, 1. This is the stress side. Remember, you have two conditions. One of them is the stress, the other is settlement. You should also calculate the settlement for this example. Any other questions so far? Some of your friends couldn't join the meeting. Okay, so let's proceed with the settlement. For the settlement, we needed the elastic settlement side. We're looking for this. settlement. We have SE and SC for consolidation, which will be 0. So it will be summation of these two. Total settlement in meters should be less than 0.05 meters. This is my condition in settlement. I have a formula for elastic settlement, but I need to obtain the stress at the middle of my soil layer. So let's go back to our figure. It was, the thickness is about 2 meters underneath the foundation. Now this is not B anymore, it's an L. So I will calculate the stress at the middle of my value. So Z will be 1 meter. For Q, calculate stress at 1 meter depth. How do I do that? I have a chart. So I should utilize this chart. I know M and N. Well, we have 3 and 9 now for our dimensions. What we will do, we will calculate little m and little m. M. Well, Z is 1. Basically. So whatever N and M is, it will be the same as our foundation. In that case, what I suggest you do, you utilize the stress on surface. Okay? Or you can utilize 2 by 1 condition, 2 by 1 rule. 2 by 1 rule. Remember, for what was this? It says if your foundation for 1 meter depth it will grow 50 centimeters from both sides. So it will be B plus Z, and the same way L plus Z. So your stress will be reduced. 2 by 1 rule, it will be B plus Z, L plus Z. Z in this case is 1. It's better to use 2 by 1 rule when you want to formulate everything on Excel and not by using the figure. It will be this one plus 1 meter. This will be equal to M plus 1 meter. at the z equal to 1. So I didn't utilize the graph. The total stress we initially found, I will recalculate this. So I can copy paste the initially conducted applied stress formula here. This time the N, let's write it again so it will be clear for you. The N will be the safe value, division with the new dimensions, open bracket, this times that, close the bracket, I will fix this. Okay. Then times, open bracket, 1 plus 6 times E over EX. 6 times E divided by the new dimension EX, which is smallest. This is your stress at the middle of sensor. Let's look it up. It's much less than what we initially found. The elastic modulus depends on our SPT. So I copy and paste here. It will be plus or equal to 500 times open bracket. It was 15 plus 15 kilopascal. However, this D dimension is on the surface. For new Poisson ratio, and we utilize sand, utilize 0.25 for fine grain. Mu equal to IF is 1.12 we initially set for the worst case scenario. 1.12, or let's calculate for the rectangular shape. L over B ratio is required. L over B. 9 divided by 3 will give you 3. So you need to go here and take something close to this 2. In between here, L over B is 3. You can do linear relationship, correlation. Let's assume 1.8 for now. Let's calculate the equal to the stress times B times open bracket 1 minus mu squared times IF divided by modulus of elasticity. Let me formulate here so that you will understand what I mean. Sum this plus that. So it doesn't satisfy my condition, as you see. Somehow I need to extend my calculation. It doesn't satisfy. Increase dimension. Any questions so far? Please connect via your microphone. Yes.
Sorry, sir.
Yes.
I didn't understand the last part.
Okay. You mean here?
Yes, sir. How did we sum the all number in the end?
Summation. I summed elastic settlement with the consolidation settlement together. Yes? So I said SE plus SC. But because it's sand, I don't have any consolidation, so it was 0. So if I had, I would calculate this here. Next question, please.
Sir,
Yes.
can you tell me about stress Q 772.5? How to get it this value?
$772 is the applied stress at the middle of your foundation depth. So if I open this again, this is your foundation. And this is L. This is B. I said the stress reduces G by 1 rule. But for 1 meter, there is an increase here at 0.5, and also here 0.5. Summation of these two will be same as Z. Why I did this is that the total thickness of the sand was 2 meters. So I need to calculate the stress at the middle of your sum. So I'm interested in the middle. Half of 2 will be 1. So by considering that 2 by 1 rule, z is equal to 1. B plus z, L plus z gives you the need dimensions, and you calculate your stress accordingly. Now, as it didn't satisfy, what I'm going to do, I will increase the B value to 5. And I expect to see a reduction instead of applied values until I reach the right figure. Okay? I made it 5 by 12. So it became 6 by 13. Just because I gave you too big value initially in actual force N, the settlement is too much here. Okay, don't get confused with the values, but just understand how changing B and L changes. Okay, any other question?
No, sir.
Okay.
Excuse me, sir.
Yes.
Sir, could you tell me which one N you used for calculating E? Is it SPTN or normal N?
This is SPTN. This N you have in
Yes.
E.
Oh, okay.
Okay, next question, please.
Okay, so what if we had a water table, like water level?
In this one, we didn't have any water table, but if we had water table, remember we used to change gamma 18. So instead of gamma 18, you would say 18 minus 9.81 and would utilize that in your formula, not this 18. Let me zoom in. Okay.
Okay.
Any other question? Okay, I will save this video now and I will post your assignment as well. If you have any question, please send me a message and we talk.